So please do ask your questions via the Q&A window on Zoom. And please post your questions throughout the presentations, and we will get to as many of them as we can at the end of each talk. We would love to hear your thoughts about our webinar series and this webinar in particular, and you can share your thoughts with us via our LinkedIn channels and Blue Sky. The tags and the handles are available on screen now. And if you would like to find out more about our Cheminar series, there is a link provided here, as well as a link to our newsletter should you wish to subscribe to further news. Before I move on to introducing our first speaker, I'd just like to spend a few minutes talking about Thieme, in case you're not aware. So Thieme is a German company with an international presence of over 130 years of experience in publishing science and medical information. And Thieme Chemistry is one of the arms within the Thieme Group itself. We have many products within Thieme Chemistry, some of which you may already be familiar with and are on the screen right now. So you may know Science of Synthesis, which is our full text resource for methods in synthetic organic chemistry. We also have Pharmaceutical Substances, which is our online knowledge base for API synthesis, patents and applications. But we are probably most well known as publishing journals, and so our titles such as Synthesis, Synlet, Organic Materials, and Synopen may well be very familiar to you. Not shown is our suite of biomedical chemistry journals as well that include Drug Research, Planta Medica, and Pharmacopsychology. And if you would like to find out more about Thieme Chemistry or our products, there is a link there on the slide for you to find out more information. As I mentioned, we are very lucky to be joined by editorial and advisory board members from Organic Materials. And since we are talking about emerging trends in organic materials today, it makes sense to highlight this particular journal, which I manage. So Organic Materials is a singly anonymized, peer-reviewed, gold open access journal from Thieme, publishing the very latest discoveries in synthesis organic materials. Naturally, it covers a very wide range of topic areas, including porous materials, crystal engineering, organic electronics, functional polymers, and many more. There is a full list of topic areas that are welcomed in the journal on that link there, just on the bottom left. I'm delighted to say that Organic Materials is abstracted and indexed in several databases, including Scopus, and the journal has a site score of 3.7. There's a QR code on the screen there, and if you'd like to find out more information about the journal, please do visit that link. At Organic Materials, we have a Best Paper Award. So this is an annual award which was recently started that awards the best research paper published in a given year based on the science presented and its impact in the field. So on the screen now are our inaugural winners from the 2023 award, and our winners are presented with a personalised certificate, and the corresponding author is given €1,000. And this is to be used for travel to a conference to help present the work that won the award. We also do quite a lot of publicity of our winners to try and showcase this excellent work within our community. And we do this on our LinkedIn, our Blue Sky channels, and kind of more generally on the website as well. And another journal that deserves an honourable mention here as well, which is related to materials, is Sustainability and Circularity Now. This is one of our newest journals at Thieme Chemistry and is also gold open access, and really looks at the most serious challenges pertaining to sustainability that we face as a community, and that as a globe, what things are of the most global interest and what we can work together to solve. So the journal really aims to facilitate scholarly, public and policy conversation across the globe to help resolve these really crucial aspects that are affecting us. So naturally, the journal is quite broad in scope. It also strongly aligns with sustainable development goals, and we actually put the individual sustainable development goals on the papers as picked by authors to help indicate to funders and to readers how this work fits in with those crucial development goals. We're available on many different channels, as seen below, and also we have a QR code there. So if you would like to find out more information about this journal, please do visit those links. So I'm delighted now to finish my section and hand over to our first speaker, Dr. Irina Stara, and I'm delighted to give a bit of an introduction. She is an advisory board member for Organic Materials and is a senior scientist and project leader at the Institute of Organic Chemistry and Biochemistry, IOCB Prague in the Czech Republic. After completing her doctoral studies at IOCB Prague, she pursued postdoctoral research with Wolfgang Opolzer at the University of Geneva. She has held visiting professorships in France and Japan and was recently awarded the title of Knight of the Order of Academic Palms, although it has a beautiful pronunciation in French, but I am unable to do it justice. That's the English name. And she was awarded this honour by the French Ministry of National Education and Youth. Her research interests include asymmetric synthesis, pi electron systems, CPO emitters, on-surface chemistry, and molecular electronics. And so I would like to hand the floor over to Dr. Stara. Thank you.
Hello, everybody. Thank you very much for a kind introduction of myself. I will share my screen at the beginning. Let me know, please, if you can see the screen.
That's great, Irina. Thank you very much.
Okay, so thank you once again for kind introduction, and thank you all people in Thieme Chemistry for organizing such a great seminar and giving me the opportunity to speak in such a great event. When I was thinking about what are the emerging trends in organic materials, I realized that undoubtedly it's integrating of chirality and P conjugating systems into new materials for electronics. And so that's why I just titled my talk Chiral P Conjugated System for Next Generation Photonics and Electronics, Circularly Polarized Luminescence and Charge Transport in Helical Aromatics. Well, why circularly polarized luminescence and why charge transport? Circularly polarized luminescence is very important for quantum communications, for optical storage data, and it's possible to say for low energy future devices. Whereas charge transport is essential for spintronics and for tunable optoelectronics devices. In my talk, I will briefly speak about helicines and how to prepare them. Then I will move to helicines as CPO emitters. And in the past part of my talk, I will mention conductivity of helicines and I will describe this phenomena in details. So first, helicines. I don't think it's really necessary to introduce helicines to this audience. I would only like to stress that they are P2 conjugated molecules, inherently chiral, unique, non-planar, and they are stable and soluble in common organic solvents. And because they have contorted shape, they have a wide possible applications in optoelectronics, as I said, sensing, enations, selective catalysis, and so on and so far. Well, how to prepare helicines? In our laboratory, we developed original approach to them, which is based on intramolecular version of 2+2+ cycloisomerization, which creates this central benzene ring within, together with these and these two rings. It means 3 rings at one within one synthetic operation, which makes a big contrast to some frequently used method, how they are, for example, photo dehydrocyclization or show reaction. Which is what is important to stress, that it is a highly exergonic reaction. It is shown in this cartoon, and it is a very robust method. It is scalable, and because of this big release of energy, it is very suitable also for construction of a strained system, and it is possible to run the asymmetric version. Nowadays, this approach is highly used in different laboratories around the world. Here, ladies and gentlemen, there are a couple of examples what structures have been prepared by 2+2+2 cycloisomerization. There are various structures you can see. They can have also heterocycles like those which incorporated sulfur. They are depicted in yellow. With nitrogen, they are depicted in green, or with oxygen, as it is shown here, which are depicted in blue. Well, I promised to tell you about helicines as promising CPL emitters. Circular polarized light, as I already mentioned, is very important for future applications like future displays, 3D displays, photonic technology, and so on. And there are different methods how to generate circularly polarized light. First, it's by physical method. It means one can take a chiral luminophore and to generate it by means of physical means. But this requires to use the anti-glare filter, and as a result, it is we can see that there is just at least 50% loss of energy. Much more better it's to generate circularly polarized luminescence directly from chiral luminophore. Well, when we started to think about this topic, we decided that the design of our new structures should compose of two parts. Luminescent part, which is just this pyrene, which is highly luminescent unit, and helicine part, which brings here chirality. So we speculated that when we make such a model and we extend the pyrene unit, extend the aromatic system, it would lead to enhance luminescent properties. So first we prepare such a helicine, which is shown here as a racemate, and we use chiral HPSPC to prepare enantiomers, and we also prepare and design and prepare another compound with incorporating this oxygen atoms, and this one was prepared by asymmetric synthesis. Here it is a crystal structure of this helicine, this chimerical pyrene heptahelicine, and you can see that these pyrene units are a little bit tilted together, and it's because of dispersion forces. Well, we measure we investigate CPL properties of these structures, and here are the results. So circular polarized luminescence means it is a different emission of left and right circular polarized light, and it is characterized, or it is just pronounced by dissymmetry factor G lum. And here it is the equation which includes intensity of left and right circular polarized light. For helicenes, the range in which dissymmetry factor G lum it's usually observed in the literature is 10 to minus 3 to 10 to minus 4. But because and I forgot to say that the range of G lum is from -2 to +2 units. And because we have different materials to compare, and dissymmetry factor will not be fully characterized, will not characterize these materials. Some authors recommend to introduce so-called brightness, CPL brightness, which has these two components, meaning that it is just the total photon included into the consideration. And for helicene, you can see usual range for CPL brightness. And what we find out for these two molecules. For this molecule, you can see that the G lum is really high value, and it's highly above the usually observed values, because it is 7.5 times 10 to minus 2. Even for this compound, the G lum is very high. And ladies and gentlemen, also, I would like to turn to your attention also to CPL brightness. In both cases, unusually high. And these compounds, as you can see here, they have very good geometry for possible formation of so-called internal excimer. And that was the question, if such a high values of G lum is really just caused by formation of this excimer. And to address this question, in collaboration with Stefan Ill from Oak Ridge National Laboratory, we ran the calculation and definitely confirmed that in this particular case, it is just the compression which is visible. And you can see that here excited state and ground state are different in colors. Ground state is in blue depicted, whereas in excited state is in yellow. And if we compare these two values, it's about 12% in excited state compression. And it is also nicely visible from HOMO-LUMO representation. Here is the ground state, here is the excited state, and again, especially in this area, you can see that the orbitals are extended through the space. So we can conclude that there is possible to form this excimer. And we went further, and we saw about some other design of the compound, not the design in which pyrines are directly incorporated into the helicene backbone, which I just described, but a bit simple model in which helicene backbone has two sigma bonds which have this as a substituent, these pyrines. Here it is in a nutshell the synthesis, and you can see that pyrene units are introduced in very last moment, in very last step of this synthesis. And we prepare the whole range of these emitters, pyrenyl based helicenes, and I will just show you this one, C2 symmetric, And we also investigated CPL emission of this C2 symmetric compound. And we found out that even though this is just the structure which has no chance to create intramolecular excimer, still you can see that G-lum stands still very high. Brightness, it's a bit lower. And then we also make a C1 symmetric compound, as you can see in this picture. And here, the pyrene units are nicely oriented just to be in close proximity. But in this case, for this C1 symmetric compound, you can see dramatic decrease of G-lum, whereas here is 2 to minus 10 to minus 2. Here it is 10 to minus 3, and also brightness is much lower. So now we are working on explanation why in this case it's so high number, and in this case not that much. Here, ladies and gentlemen, I would like to confirm what I said, just showing you UV-Vis and fluorescent spectra. Here in this first picture, you can see this compound with incorporated pyrene units, and you can see nicely there is a big Stokes shift. And what is important here is just the band which belongs to excimer band. The completely different situation is in this picture and this picture, meaning that pictures of C2 symmetric compound, C1 symmetric with only sigma bonded structures. And here you can see that the band which would be dedicated or described as excimer band, it's missing. So it is confirm what I said. So now we are trying just to rationalize our observation, because it's obvious that the commonly accepted explanation for high CPL properties are usually combined with possibility of formation of internal excimer, but here it's not the case. So we are working on it. Well, ladies and gentlemen, and now I would like just to put our experiments, our values into the context. Here you can see just the premiums, just the best molecules among small organic molecules concerning CPL emissions. And just the really very best is this compound published by Sato Isobe in 2017. And you can see our compounds definitely belongs among these 6 the most successful among small molecules concerning G-lum values. So, ladies and gentlemen, next part of my talk will be about conductivity of helicene. The question in helicene chemistry is how the charge is transmits through the molecule. If it's done just by internal PP stacking across the loop, across the space, or another possibility is just it might go, might follow the helical pathway through bonds. We decided to investigate this phenomena by using of scanning thalamic microscope break junction, which means that this tip is from gold, and it is regularly put into the contact with metal or gold surface, and just touch up, and in between it's the molecule catched, and to ensure the stable contact, it's important to have anchoring group at both ends of the molecule. Why is it important to investigate it? It's for example for cis effect. Cis effect stands for chiral induced spin selectivity, which was introduced by Roman Naman, and it means it's efficiency. It means the efficiency of electromotions to chiral molecules depends on their spin, which is important, for example, for spintronics. So we decided to study this phenomena on these two compounds. It's a heptahelicene, which bear two anchoring group in different position, 2 prime, as it is in this picture. Acetylsulfonyl groups are a little bit shifted to position 2, 3 prime, and this is shown here. We decided just to employ heptahelicene because in heptahelicene it's possible to have internal stacking of these rings, which means it allows an alternative channel through the space. And it is shown in this picture. Here you can see it is a good communication between these electrodes. It's of course simplified model, whereas in this structure the communication is a bit worse. So this is a linear P conjugated compound of the molecule, and this is it's called the cross-conjugated molecule. And we measured the conductance, and you can see here it is 3 orders of magnitude difference. Higher is in linearly conjugated molecule. So we can conclude that the path in the molecule is through the helical pathway. To confirm this, we just make the calculations, and also from the calculations is visible that linearly conjugated material is much more efficient for transmission of the charge. It is shown here in these red pictures or red arrows, whereas this cross-conjugated is much less efficient. And we can definitely conclude that even these calculations confirm the helical pathway. And it is very important observation and very interesting because it seems that the majority of the charge goes through the external rim, even though it's longer. But it is less screwed. It is better, less distorted. Is a better overlap. So helical pathway seems to be prevailing. So, ladies and gentlemen, let me conclude my talk. So first, I talk about the synthesis of helicene by 2+2+2 cycloisomerization of aromatic trianes, which is robust and scalable. Then I told you about helicene as CPL emitters, and I just stressed that the helicene might be very promising pyrene-based emitters, and they have very high G-Lum factors among the small molecules. And I also talk about conductivity of helicene, and I told you that the majority of the transmission is going through helical pathway. So wrapping up this cutting edge research, the recent advances in helicene chemistry just highlights the important potential of these molecules to become efficient and I would say a lot of versatile building blocks for next generation material, because they are light responsive, electrolyte electronically active and structurable, programmable. The future, I'd like to thank all my collaborators who were fantastic, all my colleagues from the Institute who were engaged in synthesis, analysis, computation, and NMR and ECD. Also our collaborators from University of Pisa, Francesco Zino and Rino Visitelli, Stefan Ehler from US, and also for X-ray. And I am very grateful for the financial support these organizations. And thank you once again.
Thank you very much, Irina. That was a fascinating talk. Thank you for taking us through that. I would now like to ask whether anyone has any questions for our speaker, particularly on the panel, if there's anybody who has a question. That would be great. Perhaps I can kick off then, Irina. I mean, it sounds like these helicenes are really the way of the future. How do you think things will change over the next kind of 3 to 5 years, and what will helicene's role be as part of that future?
Yeah. But what I can say that it is obvious that recently there are incredible structures being prepared, which like a couple of years ago were unthinkable. Just very complex structures, and these very complex structures always goes complicated properties and functionalities. So I would expect a big development in recently very quickly developing, and also the tools for analyzing what you prepare. So it's my expectation that the complexity of such molecules would be much higher in the just years to come.
And is that your next steps in your own research, you think, kind of increasing the complexity, or?
Yes, definitely. Yeah. And it's not really just the easy task, because we are facing the limits nowadays. So
yes,
it's necessary just to push the limits forward, to be able to think more, you know, about more risky structures and so on. But it is also demanding just to develop new methods, new approaches to the molecules. Yeah. So we are working on this, definitely.
Brilliant. I think we have a question in the chat as well. Is there any possibility to flip the one stereoisomer of helicene ring on its molecular axis to realize the other stereoisomer?
So if I understood it properly, it's about the question about what is the racemization barrier and how it can be just flipped. Well, the helicene as such, they are rather stable at room temperature. So it means that for hexahelicene, meaning they are just 6 benzene rings combined together to put the framework of the helicene, it's rather stable. But in higher temperature, it's possible to flip it. But at the temperatures which we normally work, it's we for racemization, meaning to flipping one form P to M or M to P, how it is increasing. There is some plateaus and there is some increasing, but for higher helicene, higher than, let's say, 19, 20, it's still calculations, because these molecules were not yet prepared.
Brilliant. Thank you. We probably have time for one more question. If anyone has a burning question, please just type it in the chat, or if you're a speaker. Oh, have we got one? Yes, we have. Perfect. Okay, so final question then. What is your speculation on the rationale behind the enhanced conductivity in helical structures? And how, in your opinion, does this relate to the CISS effect?
Yeah. Well, I would say that this effect is about the chirality, which is something like filter for the for the system. So it's very important to understand what is just the path of the charge through the molecule, and just spoke about it, that if there is not interrupted just way between the electrons, the conductivity is much higher. So it is linearly conjugated, cross-conjugated. And definitely we think that that this difference in conductivity, cross-conjugated, linearly conjugated, is because it confirms that it is the helical pathway, because these two molecules, cross-conjugated and linearly conjugated, it differs only in the substitution, in the position of substitution. So it means if it would be just it must be like that, because it is just very little difference in the structure, only the position of substitutes. Otherwise, it's the same. So is confirmation for the helical pathway through the molecule. Yeah. So if it's just
Fantastic. Thank you. We've just now had a couple more questions, so we'll probably ask one, and maybe we can send you some questions afterwards.
With pleasure.
Yeah. So the final question then is, what about the electric properties of helicene on the racemization or enantiomer conversion?
Well, perhaps this. Well, it's a quite interesting question, because during we can see the helicene as a spring, and this calculations were done for relax spring, but we can of course stretch or push the helix, and it definitely influence the conductivity. So when stretching in is just lower conductivity. It's there is some examples from the literature, and when stretching it even more, its conductivity, theoretical calculations tells us it's better, and it's because of the overlap of orbitals, which with long stretching, definitely a long stretching, is going to such a position that it's just a more efficient overlap.
I see. I'm just going to ask that last question, as I realized, I think someone asked this question before and I missed it, so apologies. So I'll ask this final question then. Will liquid crystallinity improve CPL emission by appropriate substitution?
It's an interesting question. Frankly speaking, we did not investigate it, so I cannot comment on it. But thank you for these questions, and all these questions, in fact.
Thank you so much. Thank you for everyone's involvement with the questions. It's brilliant. It's great to ask our speakers. Okay, so I'd like to invite our next speaker, who is Professor Onion Miljanic. So Professor Miljanic earned his PhD from UC Berkeley and completed postdoctoral work with Nobel laureate Fraser Stoddart at UCLA. His current research focuses on porous molecular crystals, dynamic combinatorial chemistry, and macrocyclic chemistry. He has authored over 90 papers and a textbook on energy and sustainability, and has received numerous awards, including an NSF Career Award and a Humboldt Fellowship. He's also a member of our editorial board for Organic Materials, and I'm delighted to welcome him to start his presentation. Thank you.
Hi, thank you very much, Charlotte, for the invitation and this introduction. And I'm very happy to present to the audience of hopefully organic materials readers, and as well as my colleagues. It's a pleasure to hear Irena's talk, and I hope I'll follow up with something hopefully as good. So let me share my slides. Do you see my presentation?
Yes, that's fantastic. Thank you, Onion.
Okay, and let me try to. Okay, and you should see the laser pointer. Okay. Okay, well, let's get started. So, yeah, it's my pleasure to present to the audience of Organic Materials colleagues and readers. I've been involved with this journal since its very beginning in 2019, and this involvement started during my Humboldt stay in Heidelberg. So it's something that I really hold very near and dear to my heart. And I'll tell you about the class of molecules that hopefully are emerging organic materials called cyclobenzones that were developed in my group right about 10 years ago. And we have since been very involved in developing this class of materials and molecules and seeing what they can be applied for. And so a lot of work in our research group has been inspired by this graph, which I'm sure you've seen. It essentially plots the annual temperature averages against the 20th century temperature average. And what you see here is that some years are cooler than the average, and they're shown in various shades of blue. The bluer, the cooler, and some are warmer than that average. And this is highlighted by these red stripes that again increase in intensity as the average deviates more and more, as the annual temperature deviates more and more from the average. And what you see here is that for the first half of the 20th century, we were kind of significantly below this average. Then right about the time of the Second World War, the temperature hovered around the average. Then kind of some oscillation happened. And then for the first time in 1978, which is incidentally the year I was born, but I assure you there is no connection, you see this red stripe. And then it started becoming more and more frequent until in the 21st century, all of the years are red, which means that all of the years are warmer than the 20th century average. And we now have a pretty thorough understanding of why that is. And these changes in our climate are caused by the changes in our atmosphere. And these are basically caused by the increased concentrations of greenhouse gases that trap the solar radiation and re-emit it, increasing the surface temperatures of Earth. Most of these gases are really minor components of our atmosphere because the major components, such as nitrogen and oxygen, contribute nothing to the greenhouse effect. But the gas that you hear probably the most about is carbon dioxide, which is the dominant greenhouse gas. And all of the other gases is kind of compared to carbon dioxide in terms of their global warming potentials, which is a relative number, which highlights how many times worse is a given gas over a 20, 100, or 500 year span. And another feature that is important are these atmospheric lifetimes. Once a gas is emitted into the atmosphere, unless it's carbon dioxide, which is a very stable molecule, these gases will eventually decompose. Many of them will decompose into carbon dioxide through oxidation. But they have atmospheric lifetimes, which vary as well. And what you see here is that there is a whole range of contributors. Among the naturally occurring gases, carbon dioxide, methane, and nitrous oxide are the most damaging ones. And then the bulk of this table, starting from HFC 23 and going all the way down, are fully synthetic fluorinated gases, which we use for a variety of aerosols and refrigerants and dielectric applications, but all have very high stability in the atmosphere and extremely high global warming potentials, hundreds of thousands of times worse than carbon dioxide. And this can be summarized in this graph, which sort of simplifies the whole thing. It shows that about 3/4 of the observed global warming can be attributed to carbon dioxide, about 1/6 to methane, and the remaining 8% to fluorinated gases and nitrous oxide. And my group has worked on capture of the fluorinated gases, but this is old work and it's all published, and we have kind of stopped working on that. So I would refer you back to literature for that. But today I'll tell you a little bit about our effort to capture carbon dioxide and methane in the pores of these cyclobenzoin molecules, as well as to highlight other ways in which these materials can be used in renewable technologies that could not capture these emissions, but contribute towards avoiding them in the first place. And so let's get into organic chemistry and organic materials, cyclobenzones are simple molecules that have for the first time been prepared by my graduate student Qing Ji, who is now a professor in China, by the benzoin condensation, so an extremely old, well-documented reaction that was discovered by Liebig himself, of in this case isophthalaldehyde, which in the presence of sodium cyanide, very simple catalyst, condenses into this molecule called cyclotribenzoin, which we would have published in Organic Materials, but Organic Materials didn't exist back then, so we published it in another Thieme journal, Synlet, which was for a long time headed by my PhD advisor, Peter Volhart. And so this cyclotribenzoin, it precipitates as a single diastereomer. This is a crystal structure, so you see this cone-shaped benzoin, which is prepared by the similar condensation of terephthalaldehyde, slightly different solvent conditions, but basically we get this cyclotetrabenzoin, which is isolated in about 20% yield as a single diastereomer. And I will point your attention to an interesting symmetry feature of this thing. This molecule has 4 stereocenters, but it's still achiral, not because it has a plane of symmetry, but because it has an S4 improper rotation axis. And this is a crystal structure on the right. Cyclotetrabenzoin inspired more work in our group since its discovery, although we're now coming back to cyclotribenzoin systems as well. And so this specific isomer of cyclotetrabenzoin is isolated because it precipitates first, right? And you can appreciate that, of course, we could have obtained various stereoisomers of this specific molecule, as well as regioisomers of the tetramers of terephthalaldehyde that are possible. And so why does this one show up as the dominant product is explained by us by its very low solubility. And the very low solubility is explained by this marvelous crystal packing, where the molecules of cyclotetrabenzoin, if you view them from the side, are organized into this nanotube, perfectly stacked on top of one another. But what is holding the nanotube together is, and so this repeats itself on each one of the 4 corners of this molecule. And so if you take these nanotubes and sort of turn them so that their opening will face you, this is what we'll see. And so this is not one layer of our structure, this is the whole structure. So it's perfectly aligned on top of one another. And because of this perfect alignment and the small cavity, we can detect a small surface area associated with these molecules, even though it's not very large. Now, this molecule, cyclotetrabenzoin, it was very pretty crystal structures and very nice to look at. However, potential as a supramolecular host in solution, we really critically needed to make it soluble. And we did that through what we thought at the time was a trivial modification, where we take a secondary alcohol and we convert it into this acetate ester. And one was expected, and that is solubility of this material has increased dramatically, so this is soluble in most organic solvents now. But also its surface area has increased also dramatically, more than 10 times. And this is because we now open up secondary pores in this molecule. And so what we see in this crystal structure is the square-shaped pore, which comes from the macrocycle itself, but the square-shaped pore is surrounded by the cycle in the solid state. And we have noticed that despite the fact that we can produce these crystals from a variety of different solvent conditions, the packing is always the same. And so this is monomorphous material. And the hydrogen bonding is now gone, but this molecule simply seems to have a very awkward shape, which permits no closer packing than the one we observed. And this is the work of my 2 former graduate students, born now in chemical industry, Corey McHale and Mohammed Hashim. Now, with linear pi electron-rich casts in the pore of this cavity, and what we see here on the left are crystal structures with carbon disulfide, so a linear molecule, acetonitrile, where you see the triple bond of acetonitrile sort of timidly protruding into the cavity, as well as propargyl alcohol, where again you see the terminal CC triple bond included in the cavity here. Now, to be completely open about this, related to the solid state. So in solution, we are still not even able to see this binding. So it seems to be relatively weak. And what we're trying to do now is co-crystallize our cyclotetrabenzoin acetate with the ultimate linear guest, and that is carbon dioxide. This sounds like a very improvised experiment, because it was. And so during her studies, she would take a single crystal of cyclotetrabenzoin acetate, put it in a small glass capillary, and then put as much dry ice as she could into that capillary before sealing this structure. So what you see here is these two different orientations. This one, which we'll call vertical one, where the carbon dioxide is stabilized by sort of equidistant pi-pi stacking with all four of the benzene rings. Occupancies of both of these positions are significantly under 100%. And so it's not that we have two molecules of carbon dioxide. It's typically one or the other in this orientation. Now, because of the fact that this cyclotetrabenzoin acetate is made in two steps, one is the benzoin condensation, which is done in water and alcohol solution. The second one is acetylation, which is done in neat acetic anhydride. This is a pretty easy and pretty scalable synthesis, and Corey was able to produce 15 grams of this material in a single batch. And so this allowed us to send it to, and he has really constructed adsorption columns filled with our material as a neat adsorbent, and use those columns to separate carbon dioxide from nitrogen and carbon dioxide from methane in these breakthrough experiments. And so these are experiments where we pass a stream of pure, of 50-50 mixture of carbon dioxide and methane or nitrogen through our crystals, and then we monitor what happens. So the gas travels through the column, and then after that time, what starts coming out is pure methane, and this pure methane flows unimpeded for the first 10 minutes. And at that point, the column is saturated with our gas mixture, and so then slowly reverts back to the 50-50 mixture. And something similar is seen in the binding of nitrogen. This makes sense because methane is not linear, so it's not included in the pores, while nitrogen is linear, interact with them very well, so it's kind of flushed out very quickly. And this is important because if you think about carbon dioxide, this is the chemical that our society, if we put together all of the plastics, I think it's around 1 gigaton. And so, but this carbon dioxide is always produced as a minor component of complex mixtures. So if you think about, flow from a coal-fired power plant, it's mostly nitrogen because we don't burn coal in a pure oxygen. And so separation of carbon dioxide from other things prior to its capture. Graduate student James Lynn has come to re-examine the non-acetylated cyclotetrabenzoin, so the parent molecule, as the platform for the sorption because it aims to produce pure propylene for polypropylene production. This current separation is done through cryogenic distillation, which is very energy consuming. And so what we see here, acetylated cyclotetrabenzoin, and still selectivity, but not nearly as high in the acetylated molecule. And through a combination of molecular dynamic simulations and powder X-ray diffraction and a synchrotron with these guests included, we have shown two things. One, while the molecule on the right has those square-shaped pores and the diamond-shaped ones, which I've shown you below, the square-shaped pores are selective, the diamond-shaped ones are not. And because of that, overall selectivity is eroded in these bindings. The other feature that facilitates in selects are relatively rigid. So if you do molecular dynamic simulation of them, there is some oscillation that you see, but the pores mostly maintain their shape throughout the simulation. In contrast, the acetylated molecule, because these pores are not held together by hydrogen bonding, but simply by the awkward shape, if you watch this video, it looks very sort of peristaltic, in that those wiggly pores are able to kind of push through the guest into the material, even though the guest may not be a perfect match. And so this really highlights the shape and the flexibility of pores. The smaller molecule, we have managed to reduce this cyclotribenzoin into this hexol. This reduction is completely diastereoselective because of the cone-shaped molecular conformation, which then permits access of the reducing agent only from one side. Is these pentamers of water molecules, which are hydrogen bonded. We could identify all of the hydrogen atoms by crystallography here. And what is included here is really interaction of our pentamer with OH groups, as well as the benzene rings coming from 6 different molecules. And so what I'm showing you here is fragments of 6 different molecules. I'll show them now in different colors of our hexol. Neither here nor there. It has hydrophobic parts and hydrophilic parts, but in the solid state, it creates a cavity which is very hydrophilic and binds these pentamer water molecules. And this has inspired to start looking at other derivatives with many OH groups. and to see whether we could expand this binding cavity so that we can bind more larger water clusters, especially clusters including about 20 water molecules. Why would we want to do that? Well, because this is sort of traits which are observed at very high pressures on the bottom of the ocean, where methane molecules included in this crystal structure of water, which has pores inside. Unfortunately, these clathrates are not stable at atmospheric pressure, so they really fall apart. But so we would like. Okay, I'll move to another short story, very short story about the cyclobenzones used now in the context of nuclear energy, nuclear waste remediation. To my two former students, Alexandra Robles, who is now at Genentech, and Maimouna Al-Rayani, who is a professor in Jeddah in Saudi Arabia, have expanded using extremely old, well-precedented chemistry of hydrozones. We can make this octahydrozones. We call them molecular octopuses or octopi. First reports of this work on this octaketone have actually appeared in Organic Materials a couple of years ago in collaboration with my good colleague and friend Ali Koskun from University of Freiburg. And what we have shown, what Alexander has shown, is that these molecules will absorb iodine from solution or vapor. And you can see this by the change of their color upon exposure to iodine vapors. Structure 1C, it has this pyridine nucleus, or 8 of them, which is critical for the binding of iodine. And so 1C will bind about almost 4.5 grams of iodine per gram of our material. And this iodine binding can happen in vapor, in solution, as well as on the interface between the two phases. So this is the aqueous, and in the binding of iodine in the treatment of nuclear reactor vessels. And so if you think about nuclear reactor vessels or waste storage vessels, they are, because of this nuclear paint, is to prevent simply chemical corrosion of the steel vessels. But this paint, because it's basically vitrified glass, it still has residual solvent, which radioactive iodine will iodinate, creating volatile iodides, which are both carcinogenic and radioactive now, and they also lead to cracking of this paint. And so we are now talking to the Department of Health, so they are expressing interest in this material as a potential binding platform for iodine. Okay, and one more vignette on using these octaketone materials as organic battery materials. Lithium-ion batteries, of course, are an expanding technology and low availability of lithium, but there are others, such as availability of cobalt and phosphate, which are used to produce electrode materials. And cobalt is especially problematic because of its mining in the Democratic Republic of the Congo, which is done very poorly regulated in terms of societal, ethical, and environmental regulation. And so switching to an organic material would really offer a more sustainable route to these electrodes. And we have tested these 3 cyclobenzones, ranging in size, as electrode materials. Why would they be good electrode materials? Well, we thought produced 8 times. And so we have tested their capacities, and they're all okay and in line with their molecular weights. But what is sharply differed is their capacity retention, meaning the stability of that capacity. And so in that respect, the central material, the reason for that is they were simply too soluble. And so these organic molecules, they would dissolve in the electrolyte, and the electrolyte is basically diethyl carbonate or some derivative thereof. And of course, if you have an electrode which dissolves in an electrolyte, it's not a very good electrode. But the reason for the lowest solubility of this naphthalene system is based on a very sort of simple introductory organic argument, and that is free rotation. And this creates disorder and increased solubility. Something similar can happen on the molecule on the right. In the molecule on the left, you have this C2 and C6 axes, which are offset from one another. And so the rotation would have to be sort of bicycling motion, which is fine if you have an acyclic molecule. But in this cyclic molecule, one of these bicycling motion cannot occur independently. It has to be coupled at least with the motion on the other side of the ring, and possibly with all 4 rings. And this leads to entropically unfavorable rotation. And so because of that, this molecule is the most rigid one. It is low as we go to reduced states. These reduced radical anions are kind of difficult to probe experimentally, and so that's why we turn to computation. And so our collaborator Judy Wu at the University of Houston has shown that indeed rigidification occurs during reduction, because as we place more, can be that is more rigid than the starting material, so the solubility doesn't increase. And this work was published a couple of years ago, and we were happy to get a feature on the cover. All right, well, this brings me more or less to the end of my talk. So I'll show you some simple organic chemistry, which maybe highlight where these molecules are going. If we take the cyclotetrabenzyl and heat it in molten urea as the solvent, what results is this condensation into a 4-fold cycloglycolurea. And so we don't really know what to do with these molecules just yet, but we're hoping to find, this is sort of a hammer in search of a nail problem, and something similar works on the smaller trimer, and we have done a lot of work on the crystallography of that. A group of students in the past 15 years at the University of Houston, and so their names I have tried to mention as I spoke about individual projects, but here they are all in one place. I have been also delighted to work with a range of collaborators around the world, and most of this work has been supported by the National Science Foundation, as well as by the Welsh Foundation, which is a philanthropic. And so if you're a chemist in Texas like myself, then this foundation is very dear to you. And of course, my involvement with Thieme and organic materials really probably would not have happened without the help of Alexander von Humboldt Foundation, and so they're gratefully acknowledged here as well. That's all I had for this morning in the US and afternoon in Germany. So I'm happy to answer questions if you have some.
Thank you very much, Anja. What a great talk. And yeah, I really enjoyed the sustainability aspects of everything that you were doing there as well. Obviously, that relates to the other journal that you're part of, the advisory board for SC now. So yeah, thank you so much for taking us through all that fantastic work. Of cyclotetrabenzyl.
Right, yes, I can. So cyclotetrabenzyl, if we're referring to this octaketone, is actually a reasonably soluble organic molecule. So it's soluble in chloroform, dichloromethane, not soluble in hexane, but it's significantly more soluble than cyclotetrabenzoin. So it's non-reduced.
Great. And our second question comes from one of our other speakers, Max von Dielis. So he says, great work, Onion. Have you or alcohol functionalities?
Yes, thank you very much for the question, Max. Yes, we have thought about it a lot, and we have a lot of projects aimed at doing both coughs and, for lack of a better word, sort of pi stacked organic frameworks. But as I think this audience is quite familiar with a lot of cough work, there's really nothing to report until there is something really big to report all of a sudden.
I see. Brilliant. Well, thank you so much, Onion, for a fantastic talk. I would like to invite our next speaker to start their presentation, and I will just give a brief overview. So this is Professor Max von Dielis, who will be talking to us next. Max is one of our advisory board members since 2016, he has led a research group at Ulm University, working at the interface of systems chemistry, supramolecular chemistry, and functional organic materials. So it's a pleasure to welcome Max to speak as part of this special session. Thank you.
Thank you, Charlie, for the kind introduction. It's been a great pleasure to work before. And I will start with a quick introduction with our research portfolio. At the top, you see some work on systems chemistry, like Ognian. That is perhaps the most interesting. So new tools in dynamic covalent chemistry, supramolecular polymers, curved pi systems, mechanically interlocked materials, and lately some open shell molecules and materials. I do want to advertise 2 of our papers in organic materials on compounds and on ASA CPPs for C60 binding. So today's talk will be at the interface of our activities in nanohoop synthesis and dye radical synthesis, which we actually kind of stumbled into, if I'm to be honest. So the introduction is probably well known to many of you. Especially I like this quote by a former professor at MIT. Of course, we live in a material world, as many musicians have already told us, but we really live in a materials limited world, and basically knots and ropes to mechanical computing devices from wood and metal to hybrids of mechanical electrical computing, and then of course transistors, vacuum tubes, later silicon chips, and now of course quantum computing. So the most powerful quantum computers, and this is not widely known or not enough widely known, they would require a ridiculous amount of space and actually also energy for the cooling if we were to scale them up to millions of qubits. Making molecular quantum computing devices, so basically using molecules for the superimposed spin states that quantum computing really requires. I think to many of us, this is a great challenge. And molecules are, of course, tunable, and in principle, they are scalable. So, 1 million of molecules, that's not a lot. So actually, a lot of the terms of scalability and so on, they mean something completely different once you enter this field. For this talk, I want to highlight really the spin optical aspect. So a molecular quantum computer, if it ever exists one day, it will be operated with light. So the qubit, where I will focus on rings. And I really like this Nietzsche quote, "What does not kill me makes me stronger," for highly strained curved macrocycles. You can get some really remarkable properties from bending pi systems. And this is one example work we will just submit in the next few days, where this was the case now in the molecular qubit area. So here we are in a research community about putting porphyrins into rings. And in 2019, we reported the smallest and most strained cycloparaffenylene porphyrin hybrid macrocycle. And we observed some very interesting redshift in the UV spectrum. We saw that only nickel porphyrins actually survive this crazy strain energy of 50 kilocalorie per mole. And we used this to bind fullerenes, our favorite gas. We also made bigger ones, but we didn't really care about them at the time. So Xing Mao, postdoc in my lab, I asked him to make a copper porphyrin macrocycle, which is not extremely strained. So we have 3 porphyrins now linked through these anthracene phenylene bridges. The copper porphyrins were chosen because they have spin fast. Purification is very important in this field. So Xing Mao did some great work with preparative HPLC, and we always check via several techniques that our compounds are pure. Xing Mao had good hands, so he grew single crystals, which in synchrotron radiation, we got this beautiful X-ray structure. So you see it's really a nicely circular shape, 3 porphyrins bent together. You see already for a copper porphyrin, this is actually already quite bent. So we see signs of strain in this X-ray size, location, and orientation. And this is really, I believe, what the nanohoops will hopefully have something to contribute in the next decades or so in quantum information processing. UV absorption, we see the usual redshift. So this redshift, DUC CPTA, the blue curve, this is the nanohoop. And there's now these non-strained reference macrocycles, basically precursors in the synthesis, which don't show this redshift. We got some transient absorption data from a group of Benjamin Dietzek, Ivancic in Jena and Leipzig. And the take-home message is there's no light. How important to explain something in a moment. We teamed up with Sabine Richard, now moving to Frankfurt University, to study the EPR with her postdoc Ashley Redman. And they observed relatively typical copper spectra, EPR spectra for copper porphyrins. Although you already see here, there's some rather pronounced differences between these three species which carry strain. So the really interesting results began with when Sabine studied now the dipolar coupling between spin centers. And she saw that only in the nanohoop is she able to record this really well-behaved Rabi oscillation, which actually allows you to measure the distance between the copper centers, which basically by shining light on the molecule. So this is exactly what the physicists are most interested in this field, that the molecular qubit can be initialized with light, and which currently at room temperature is only possible with these very ill-defined nitrogen vacancy centers. We are not at room temperature here, but still we believe this result is very interesting and important. So on the right, you see that the spectrum then in the end with this transient EPR is the same as if you do the traditional EPR spectrum. Only in the blue case, it has really come to life with light, with a light pulse. So this photo-induced spin polarized ground state, I believe, is something very interesting, and that we saw it now in this rigidified nanohoop, I think is a very interesting result. So now I'm going to jump to the second part of the talk, which is on radicals. And here I have a quote. It's actually not really precise, by Martin Luther King. Let's build bridges. So in chemistry, we should always build bridges. And in this case, we build bridges between radicals. So here we are in a field where the old work goes back really long, into 1900. Moses Gomberg citing the work by Friedel Crafts and even Emil Fischer. So the giants were really having a go here with trityl compounds. So the Gomberg radical, of course, we know now dimerizes through the para position. Very important work by Ballesta starting 1971 was blocking the para position with chlorine atoms and also kinetically stabilizing such trityl radicals. So this also goes back a long time. And now lots of people around the world are trying to assemble kinetically stabilized trityl radicals in 2D, 3D, or in even discrete coordination cages. So Xingmao again here, he was about to do something different. If you look at the reaction arrow, you see this is cross-coupling. The starting material was supplied by my colleague Alexander Kühne. And Xingmao noticed he gets this blue spot on the TLC. Blue, of course, to an organic chemist, especially organic materials chemist, that is something you should not ignore easily. So fortunately, he didn't. He realized quickly this is homocoupling, and Xingmao was quick to optimize the homocoupling and also to make sure this is not copper. The blue color here is really the molecule. This is not due to residual copper. Xingmao then showed me a literature overview, and I actually in the beginning couldn't quite believe it because I really thought this kind of molecule must be known in the year 2024. But it turned out in this whole zoo of other diradicals, some of them were revisited in 2023, the molecule was missing. And we knew from the beginning, from the blue color, it is very, very different from the compounds in the literature. So it obviously redshifted even compared to the Müller diradical, which has a longer conjugation chain, and compared to the Thiele diradical, which is not even a diradical really, because it's just quinoidal. So Xingmao made these three compounds, optimized the synthesis 70% yield of this new trityl diradical and the monoradical for reference here as well. So purity, as I said before, is very important. We did also ascertain this as much as we could. As we later found that light can actually lead to some degradation. We ascertain the purity of these radicals, which is important because NMR is not really your friend here. Again, Xingmao managed to grow single crystals. And you notice, I want to point out here, the bridge is completely flat. So I say that the compound has hydrogen and chlorine atoms in just the right positions. And the bond lengths here speak in favor of in-between quinoidal and benzenoid forms. So we also calculated a diradical character of 0.6. So 60% we can imagine is the diradical, 40% is the closed shell crinoidal species. So that's very, very interesting. So you have an extended conjugation path, but we don't fully fall into the boring crinoidal structure. This has probably two reasons. It's because too much aromaticity would have to be sacrificed in these two linked phenylene rings if we put them in the crinoidal form, but also the chlorine atoms tilt these carbon centers, these radical centers, by 35 degrees already somewhat out of conjugation. So there's not as much to be gained from the crinoidal form. Really one of the most beautiful CV electrochemistry that I've ever seen in my life. So the two trityl centers, they clearly talk to each other. So subsequently we can oxidize or reduce them. Hopefully there will be some interesting applications of this beautiful electrochemistry we see here. The optical properties, just very briefly, are interesting too. We have this massive redshift emission in the NIR already. You see here almost 800 nanometers. The quantum yields are quite low, below 1%. So we're obviously working at increasing these. Compared to the simple monoradical, at least there's not a large drop to be seen here. So very interesting emission and absorption in a range that none of the other radicals or diradicals really occupy. So that can be something useful in the future. Of course, together with my colleague in physics here, Fedo Jelecko, we studied EPR properties, and you see the diradical here jumps out of this in comparison with the monoradical references. The peak is much, much broader in solution at room temperature. Pulling it down, we can kind of isolate the diradical signature. And in this quick movie of VT EPR, you see that the broad shape of the EPR at room temperature is really due to spectral averaging, which we are familiar with from NMR, of course. So VT EPR and VT Squid, now in collaboration with Joris van Slageren in Stuttgart University, allowed us to determine a singlet-triplet gap. So the molecule has a singlet ground state. There's a 3 kilocalorie singlet-triplet gap. Fortunately, it's very consistent between the two methods. And finally, maybe one thing I want to point out is the stability. So we took some time studying the persistence, I should maybe say. So how persistent is this kind of chichibabin radical really? And it turned out really, really persistent in the dark. So this is 50 days, almost no drop in the UV vis spectrum. And we will clearly see any degradation here in the UV vis. So in the dark, you can really trust this molecule to be persistent. And this is in solution under air with moisture. So these are really bench conditions except for the missing light. If we add now bench conditions, so with some sunlight, we do see degradation over days. But the half-life is even 9 days in the presence of sunlight. So these molecules are really remarkably persistent. Now putting the result back into context, this zoo of radicals, of diradicals, the chichibabin type diradical that Xingmao discovered accidentally, is really unique because it has this lambda max of absorption of 600 nanometer, emission at 800, which is redshifted compared to anything else out there. And it's really having these hydrogen and chlorine atoms in just the right places. And to some extent, I would also argue the bridge is really the star of this study here, rather than really the radical. Because it was just accepted yesterday, I'm also happy to give a quick outlook. Vivek, another postdoc, he already looked into carbazole derivatives, which is obviously an increase about a factor 3. Much more will be difficult here, but that's already definitely encouraging. And I do want to say we have quite a few future plans with these kind of compounds, so hopefully there will be more to come. With this, I'd like to thank the group, again, Thieme, for setting up this seminar. Again, the two postdocs whose work I've shown here there's quite a few other people who helped and collaborators as well. Hopefully soon there will be good news from a big consortium in Germany funded, where we hope to pursue this kind of research further. Yeah, and I would be very happy to answer your questions if you have any.
Thank you very much, Max. That was a beautiful presentation. If you have any questions in the chat, please do put them in. And also for the panel, if you have any questions for your molecules that you were just presenting, what are those plans? Can you tell us anything about what's coming up?
Yes, sure. So here, this very first follow-up work is on increasing the quantum yields. That's important, but something else actually is a lot more important. And this is to actually make diradicals, which not only interact with light, emit light, but have actually a triplet ground state. So this is definitely something on a lot of people's mind.
Yeah.
This will be very interesting. Who will be first with that?
Yeah.
Definitely high emission quantum yields will be good and important, because if you want to read out small arrays of qubits, it's actually a bit of a problem to have only a 1% quantum yield. You definitely want to be higher than 10%. With the before to integrate these into larger arrays, actually, because it's nice to have 3 spin centers in a macrocycle, but in many ways that's not enough. So it would be nice to have something we call hierarchical assembly or self-assembly to really bring quite a lot more molecular qubits and spin centers together. Yeah. So that's enough for the moment. Yeah. Quite a lot of plans.
A lot of exciting detailed plans there, my goodness. Excellent. So we have another question just in the chat here. So great talk. This person says, has the role of conjugation in the diradical stability, and more specifically the extent of conjugation across the chain length, been explored?
Yes, not so much by us though. So here we really lean on these literature comparisons. I guess one thing we explored ourselves, and here the credit goes to my colleague Alexander Kühne and his student Julia Zolk. So they calculated our molecule, or molecules now, I should say, with TD-DFT calculation. So we do understand why this bridge is so special. We do understand even the transition states, so we did not just calculate HOMO and LUMO, but the S0, S1, and the triplet states. So we do understand this very well. The Thiele radical is not really a radical. It's completely benzenoid. And the reason for that is mainly that there's only this one phenylene here. So we only sacrifice one aromaticity energy here. And for us, for our molecule to go into that state mainly, I mean, it's in that state for 40% fraction, basically. This would just cost too much aromaticity. The Müller diradical is interesting. It's longer, so you would expect a redshift. But what happens is that these phenylines to the central phenylene, they are tilting out of planarity. We see what is normal for oligophenylines, that there's a dihedral angle that is tilted on average in solution and even in the solid state. So that explains why the Müller diradical here reported in 2023 has much blue shifted optical properties compared to our compound. And now a bit more trivial is Ballesteros compound here, which is the most similar to our compound. Here the chlorine atoms pointing to the inside are forcing the molecule to tilt and preventing the conjugation, which we like very much. And so, yeah, it is lucky finding. Did not plan this.
Brilliant. Okay, if there are no more questions for Max, then I think we'll leave it there. Thank you again for Max for the presentation. And I would like to invite our final speaker up to present, and this is Professor Paul Berzinius, who is an executive editor on organic materials as well. Professor Berzinius studied in Vienna and Glasgow, completed his PhD at the University of Strathclyde, and was a Marie Curie Fellow in Eindhoven. He began his independent research in Münster in 2011 and joined Mainz University in 2015. His work focuses on supramolecular biomaterials and functional macromolecular systems. And so I'd love to invite Paul to come and close us out with the final presentation. Thank you.
Thanks, Charlie. Thank you very much. I'll just start sharing the screen.
Love your background as well, Paul. Very on brand.
I went for the home.
I can't see the pointer.
Okay. I can try without the pointer as well.
We've got a couple of minutes if you want to try and find it.
Yeah, it's just because of this sharing option that I probably let me just no, I can't get it right anyway.
So we're seeing your presenter view here.
Yeah, exactly. But I was trying to move it around, but it doesn't. So this is what happens. Let me just. I'll switch it back, and then we'll try without presenter.
So I can't see your slides anymore. It was all going so well, technically.
Yeah.
Okay. So I can see your slides, just not in the presenter view. But oh, yeah, there we go.
Okay.
Your slides look great.
Still no pointer. Still no pointer.
Oh, no pointer.
No, that's okay. I'll just get started. Otherwise, we eat away at too much of the presenter's time, and I can feel the pressure anyway as a last speaker to stick to the time. So thanks, Charlie, and your team for setting up this brilliant seminar, and also thanks to the other speakers for a really beautiful sense that also for me this is an unusual presentation because it's chemistry that we engage with fairly recently. That's and I've never presented this at least outside of Mainz. And the second reason why this is a little bit unusual is that you can see in the reference on the first slide that the chemistry we've only started to publish last year. That first publication that came out, actually the PhD student that carried out the work also carries the co-corresponding author star because she designed and performed a large part of the research. So she took the responsibility as a second corresponding author, which doesn't happen too often. So it's a small story I'd like to share that we started to do on using host gas chemistry, more specifically cucurbitular chemistry, to synthesize, to design and synthesize hydrogel matrices for 3D bioprinting and bioinks. It's a little bit too early for the acknowledgements, but still it's an extremely important slide. The people that contributed to some of the chemistry, obviously, Dr. Yuqing Wang, now she graduated last summer. In the middle here, we started to have a tradition about 2 years ago in the group that we visit companies in the surrounding of Mainz, which is always fun. And this is a group picture that emerged from this. There's a couple of people from the group now that carry on some of that work. Camilla and Marius are highlighted here. And then there's one person missing on the group picture, and that is Alex Bimmerman, who was a bachelor student at the time, who also contributed at the second. Lots of our designs and the way we think about chemistry and materials, and especially using the tools of supramolecular chemistry. I just happened to be a spokesperson of a graduate school, DFG funded graduate school that we have in Mainz on soft matter and soft materials. Somebody is drawing on my slide. Anyway, I don't know, it remains there. I'm not sure you can see this, but I can see it cross on my screen now. Can you see this as well?
Yeah, I can see it. I don't know how that's happened.
It doesn't. Yeah, it doesn't. I don't know. Maybe someone didn't agree with some of the statements. Anyway, What I wanted to say was that I think there's been a clear paradigm shift in the sense that chemists have started to realize that if you want to implement materials aspects, then it's not good enough just to think about the molecular interaction and conformational freedom of the molecules that you use, but it's also about how those entities then pack, and this becomes extremely important when you then think about property relationships, and this requires really a new way of thinking, and we collaborate very closely with our dear colleagues in soft matter physics here in Mainz, as well as the Max Planck Institute for Polymer Chemistry, and this really drives some of the design criteria in our local graduate school on soft matter. And as I mentioned, this is also a strong design criterion in my group, similar to Max. So I'll show on a very busy slide some of the portfolio that we have established over the last couple of years. Very often these days, I talk about what is shown on the top left of the slide. So using glycopeptides as fully synthetic vaccines, obviously because in Mainz we have a large hub, very visible, worldwide visible hub on immune therapy these days, and we use the toolbox of, or combine the toolbox of organic chemistry, bioorganic chemistry with supermolecular chemistry to make those vaccines. That's not something I would talk at all about. We are very busy, or have been very busy, in the peptide assembly and macromolecular assembly field. In the graduate school, we specifically use interfaces to control structure formation of soft matter and the pathways that are involved. And fairly recently, we also engaged in some sustainability aspects on more polymeric, classic covalent polymers, and use that becomes very useful in this context, but it's again not something I will talk about at all today. And the first story that I will, or the only story I want to share today, is on bioprinting. As I mentioned, the connectivities that we use to make the 3D networks and the hydrogels for those matrices and bioinks use host gas chemistry, cucurbitryl chemistry. Why did we start to engage in this field? It's not something we have done before. It's partially due to a collaborative research center 1551 on using a polymer function in a cellular context, and this brings me together with Julian König, who's a biologist, really an expert on functional genomics, together with Friederike Schmidt in soft matter physics, and we come in from the biomimetic supermolecular polymer design, the switchability and the pathway complexity, powerful in our view. I think at this, the cucurbitryls don't need a long introduction to this audience, but I'll mention it very briefly. The glycoaryl unit you have already seen in the beautiful and elegant examples of onion. So the cucurbitryls are nothing but a condensation product of glycoaryl with formaldehyde. The condensation product, you get rings of different sizes which can be separated. These days they are commercially available. Orange Sherman happens to be on our advisory board as well. So they're cyclic molecules. What makes them exciting and why we use them is because of the carbonyl, the basic carbonyl units at the periphery. They tend to bind cationic gas fairly strongly, and you then modulate the stability of those complexes by playing around with typical tools that the supermolecular chemist likes using, so hydrophilic, hydrophobic balance, as well as charge complementarity, which can be used. And what I will be focusing on is the cucurbitryl, or the CB8 unit, which has a fairly large cavity, so you can make homoternary and heteroternary complexes, in the sense that two gas fit into the same or different gas fit into the cavity of that unit. Just a few words about bioprinting. What we are interested is to use an extrusion-based process. You need to, in a way, the multi-parameter space, the challenges you need to address is the mechanical or rheological properties to make your material printable, stable enough, but still dynamic enough to make it printable, and at the same time address biochemical and chemical cues to make the material biocompatible. So in a sense, in this 2D diagram, in this very simple case, you want to move up to the upper right corner to make the ideal or an optimized bio ink. There's a few use using supramolecular chemistry. The idea of multi-componency using multiple building blocks becomes very appealing. We don't work yet on hybrids or composites, but so what I will focus on today are those interpenetrating networks where we have two different components in the connectivity, and this gives us some useful handle on defining the network properties and the dynamic properties. And obviously, it's not just two components, but the connectivity is dynamic. So it's combining those two aspects that are shown on the right. We use macromonomers to do so. The chemical entities will be shown on the next slide. Cocobitriol, it's a polyethylene glycol backbone. It's very hydrophilic, very water soluble, very biocompatible as well. And then you end functionalize those polyethylene glycol four-arm star pegs, as they are referred to. They're multifunctional, so every chemical entity leads to a cross-linking site. And this is where CB8 comes into place. We use GGF, so glycine, glycine, phenylalanine motifs, which likes to bind, and the other unit that we like to use is a stilbazolium unit for reasons that are also already shown on this slide, because this then becomes light responsive, and we can do a stepwise processing of this hydrogel matrix. These are determined by the on-off rate of that supramolecular bond, and this is something we can determine by doing shear rheology of the hydrogels when they are produced. The lifetime of if you take a tripeptide glycine, glycine, phenylalanine homoternary complex in the cavity of CB8, that lifetime of the bond is about 100 milliseconds. For the stilbazolium unit, as you will see soon, it's in about an order of magnitude more robust in terms of kinetics, not in terms of thermodynamics, but in terms of kinetics. And that lower bond, that lower handle, you can then fixate, and you go from then a physical dynamic crosslink to a chemical covalent crosslink that, at least on the timescale of the typical rheological experiment, cannot be broken. A tiny little bit of synthesis is actually fairly simple. Peptide chemistry is our daily business, so making a tripeptide is very simple. What is shown here again is the solid phase peptide synthesis approach to make an FMOC protected phenylalanine. We use star pegs, as I already mentioned, four-arm star pegs, which are activated via a chloroformate chemistry, and then turned into urethanes via either the nucleophilic amine that is still, tripeptide that is still FMOC protected, and then deprotected in the final step to get that compound on the left, or the other option that you have is condensation into the stilbazolium unit, deprotection, Bock deprotection, and then the same trick using a nucleophilic stilbene or stilbazolium unit to functionalize star peg. This is a very honest, and then I want to make this very transparent, that the isolated yields are shown, and also the degree of functionalization of the four-arm star pegs is also shown, because this is important for the network properties that we get afterwards, and we do not reach 100% functionality, because this reaction needs to happen 4 times on one molecule. But for all of the chemistry that we are doing, this is completely fine. So I'd just like to show how pure these materials are and what we can do with those. So the nice thing about using the CB8 unit is now shown on the next slide. In terms of photochemistry, if you take a stilbene or the stilbazolium unit, there's 2 things that can happen if you hit this with light, and I'm sorry, there's a little bit of information missing. Stable E configuration can isomerize to the less stable Z conformation. That's the one thing that can happen. What we want to happen is the dimerization. The dimerization. In solution, you can follow this reaction with NMR now, and this NMR data shows the chemical shifts as you irradiate in the absence of cucurbitryl, what you start to see is with time, as you irradiate, the shift or the population of the species, the trans-stilbosolium unit goes down. That makes sense. What you start to see is the cis-stilbosolium appear, but then disappear again as you accumulate more and more of the cycloadducts in solution, which is now shown in reddish color. You can confirm this if you do UV spectroscopy. I mean, this is in a way is also known. In the absence of CB8, you see appearance of the cis isomer, which then is transferred through the cycloagat, the dimer, shown the tradition with the transition is about 220, 225 nanometers. And the important information here that this transition is very slow. It's very slow, and it takes, if you keep hitting it with light, it needs a couple of hours. If you add CP8, it's done within a couple of minutes. So within the cavity of CB8, this cycle addition is done. Happens extremely quickly, which is exactly what we want for the network formation that we will be doing, or that Yuki has done. I also would like to point out that some of this chemistry, there's some precedents, and I really would like to highlight the work of Matt Weber at Notre Dame, who spearheaded some of this chemistry also for conjugation of PEG polymers and hydrogels. So what happens in terms of rheological properties, or if you take a 5% star PEG solution functionalized with the FGG unit, this material flows. That's what you can see by naked eye, basically. The same thing is true for the stilbosolium unit. If you add CB8 to either of those solutions, you start to see that it's not a free-flowing solution anymore, as you would expect in picture C and D for a hydrogel. If you hit it with light, it doesn't change. The peculiar thing is if you take the stilbosolium unit on the PEG and you hit it with light for 1 hour, that doesn't seem to be enough or long enough to get effect, because you can extract a little bit on the time scales of that dynamic exchange from rheology, which turns out to be a very important information. So if you look at the red data points, G prime and G double prime storage are loss modulus. As soon as they start to cross, that's something that is shown here, this crossing point in the frequency sweep in shear rheology, this gives you an idea about the lifetime of that supramolecular connectivity or the supramolecular bond. And that's already something that I gave away on the introduction slides, about 100 milliseconds as critical lifetime. For the stilbosolium unit, it's kinetically a little bit more robust by about an order of magnitude. If you then change light, shine light on this material, then the rheological behavior changes completely. In the dark reddish colors, what you start to see is that there's a plateau value over the whole frequency range that we examined here, at least, and this really tells you that you go from a material that is goes from a viscous component to a more solid-like property, and this happens more efficiently if CB8 is present in the solution. Because if you look at the orange data points without CB8, you do get network formation, but the network is much weaker than compared to the presence of the supramolecular crosslinker. Now, the neat thing is that you can mix, right? So you can mix FGG, so tripeptide functionalized star pegs with stilbosolium functionalized star pegs. And what you see here is now a rheology graph before you, in presence of CB8, but before you shine light on that solution. And this is basically, so going from 100% tripeptide to 100% stilbosolium, and it's nothing but a superposition of the individual. Can hit a sweet spot where you do get some physical crosslinks that are non-reversible in combination with a dynamic character, and this is in between, so going from 3 to 1 to 1 to 3 ratio. That's exactly where that range is, where you can still operate with different degrees of covalent fixation. Let's call it fixation of the network. And this has consequences that are very important. The reason they're important is, and that I've shown on the graph here, is in terms of network dynamics. So typically the rheologists would talk about shear stress or stress relaxation, so the time it takes for a material to relax back to its original state when you apply strain. And I'd just like to highlight the beautiful work of Elisha Krieg in Dresden, who worked on DNA hydrogel materials, who published this beautiful Nature Nanotechnology paper a while ago, where the idea was that if you compare biological tissues to in this viscoelastic regime, you can really go from a material that is more fluid-like to one that is more solid-like if you play around with the dynamics of the network. So it's not the degree of functionalization, degree of cross-linking, it's the dynamics that dominate the network properties. And this is now something that we can mimic with these very simple FTG osteobasolium units, where about 50% is physically cross-linked, so it's pure supramolecular in nature, very dynamic. Still the same FTG remains dynamic. You have a bond dynamic of about 100 milliseconds as lifetime. And the other 50% are permanently cross-linked via the photochemistry of the still basolium. So what you start to see is that you go from before you hit it with light, before you fixate that material, super fast relaxation, below a second, which is too fast essentially to print, because you don't have shape stability. And if you hit this with light, you move to the upper right corner. So it's still a dynamic material, but that has some solid contribution and makes it printable. The cells turn out to be very happy in this. Matrix. We can do functional assays. This is now just a couple of pictures showing that these can be printed. Now they are hydrogel at either at room temperature or at temperatures of the cell incubator, 37 degrees. The reason why you can print this is because as you apply high strain, it starts to flow. So without strain, you have G prime is higher than G double prime. So by definition, it's a hydrogel. But then if you look at this graph, you apply more than 100% strain, G prime and G double prime cross. So the viscous material properties, dominate. It flows. And this is the reason why these can be printed. So you can prepare the material, mix them with cells, and then print in commercially available 3D printing devices. And then now these are osteoblasts, and you can do very simple activity tests, crystallization tests to see that these cells still produce calcite as they should, as osteoblasts. I'm looking a little bit at the time. Organic chemistry, very simple functionalization of star-shaped polyethylene glycol macromers or macromonomers, which are then connected via CB8 mediated host gas chemistry to form 3D networks, and through photochemical cross-linking of a small fraction of these supramolecular units, you can play around with the stability, but as well as the dynamic characteristics of the network, and they can be applied, and apparently they seem to be very cytocompatible and bioprintable. We haven't included any cell adhesion motifs at all so far, so it's actually amazing that they are so compatible with cells. We were a little bit surprised, but having supramolecular connectivities, it's you don't need to be amazingly creative to think about the next step, what we will be doing. I want to thank an amazing group. That's a picture I showed at the start. A huge thank you to Yuki, who started all of this work. We have been very fortunate with funding agencies, but the same as comment as Max. Obviously, we are anxiously waiting for the 22nd of May and see the decision of, and I'm sure that the FG will be making very wise decisions. And we hopefully we'll be able to celebrate. And with that, I'll close. While the audience still thinks about potential questions, I'll just move this forward and a random selection of exciting organic materials papers. It's a random selection, but obviously I like them very much. So thanks, Charlie. I can see that your camera is on. Thanks, Charlie. And thanks to the audience for hanging around. Thank you.
So yeah, while we wait for some questions to come in from the panel or from our audience. So you were talking about the cell motif aspect of things not being incorporated. I know you said it's a natural, you were talking about natural next steps. I'm assuming that's it, right? You're going to look to do some incorporation there?
Yes, that was the initial plan. Let me just go back, but now it's frozen again. Yeah, it's frozen again. Let me just go back because what I haven't said so far is, no, it doesn't like me. What I haven't, yeah, it's, anyway, I'll just mention it without showing slides. Initially, what Yuki wanted to do was, and this was a larger program that we have funded via the European ERC grant on supramolecular engineering of glycan-decorated materials. Glycans dial those into the matrix, yeah. But so far, we didn't need to do this because the sort of naked polyethylene glycol somehow interacts with the cells. I suspect that the cucurbitals are not completely innocent. So if you ask me for my opinion why they work so well, I suspect that some of these growth factors that are in the cell medium interact a little bit with the supramolecular connectivities, and this is enough to have to turn us sort of repelling for cells, right? But so I suspect that this combination of cucurbital chemistry and cell growth medium and growth factors, there's some interactions there, but that we have not elaborated on or looked at.
Okay, interesting. Any other questions from our audience? Let's wait a couple of minutes, see if there are any further thoughts come in. Okay. Well, perhaps if there are any further questions after the presentations, if anyone thinks of something later on, if you want to email the journal, we would certainly be happy to pass them on to the speakers.
How much equivalent of cucurbitol is required, actually? Yeah, that's a tricky one because we operate right at the edge of the solubility of CB8. CB8 is beautiful. Sometimes the solubility is limiting. So the processing protocol and the way you mix and the way you prepare the material is critical. And we try to go for the exact stoichiometry that in a way that we do not have excess host in the matrix, because if the stoichiometry is off, then this has a negative influence on the network connectivity. So then but it's not trivial to get this right. But ideally, you would want to be in a 1-to-2 situation in terms of molar equivalent. But that's a challenge also in combination with the polyethylene glycol that's very hygroscopic. So it's very valid, a very good question in terms of.
I missed it. It's not updating very frequently on my side, so apologies for that. Yeah, thank you everyone for being part of today's presentation. As I say, if there are any further questions for any of our speakers, just do get in touch with us and we'll be happy to pass them along. At this point in time, all that's left is to say thank you again to all of our speakers for being part of this event. Thank you very much for everyone for attending. The recording will be circulated to participants shortly after this meeting, I think within the next couple of days. So if you'd like to watch it again, feel free to. Otherwise, we will see you at the next webinar.